video, let us study about stationary and correlation defined with respect to random processes. Let us discuss about the stationary random processes. When the expectations are invariant with changes in time, they are said to be stationary. Even the PDF also remains invariant with changes in time. Stationary of order n means that a multivariate PD of order n is invariant with an arbitrary shift in time Ts, that is fx t1 plus ts, x t2 plus ts, so on up to x tn plus ts of x1, x2, so on up to xn is equal to fx t1, x t2, so on up to x of tn of x1, x2, x3, so on up to xn. Stationary of order 1 implies now that fx t plus ts of x is equal to fx of t of x, that is fx of x, that the PDF. The PDF is independent of any time shift, hence it is independent of time altogether. This means the mean and the variance of random process remains constant. Therefore, mu x of t can be generalized as mu x. Sigma x square xt is equal to sigma x square, that is the variance of x. Let us consider the order as 2. So let us find out stationary of order 2, that is fx t1 plus ts, x t2 plus ts of x1, x2 is equal to fx t1, x t2 of x1, x2. Let us apply the invariance of time shifting, and we can write this as t1 plus ts is equal to t, where t is arbitrary within plus or minus infinity. t2 plus ts is equal to t2 plus t minus t1, that is t plus t2 minus t1, that is t plus tau. So this equation turns out to be fx t1 x t2 x1, x2 is equal to fx t plus tau of x1, x2. From this equation, we can conclude that the bivariate PDF of random process depends not only on the difference, it depends only on time difference tau, not on absolute time t. Joint stationary of order 2 for the random process x of t and y of t are defined as fx t1 plus ts, y t2 plus ts of x1, y2 is equal to fx t1, y t2, x1, y2 and is equal to fx t, y t plus tau of x1, y2. Strict sense stationary is a designation used when for any n fx t1 plus ts, x t2 plus ts, so on up to x tn plus ts of x1, x2 up to xn is equal to fx t1, x t2 up to xtn of x1, x2 up to xn applies. The most useful case of stationary is in defining two expectations. They are expectation of x of t, that is equal to mu x, expectation of x of t into x of t2 is equal to expectation of x of t multiplied by x of t plus tau. From the earlier discussions, we can conclude that the mean of wide-sense stationary random process remains constant. The correlation of wide-sense stationary random process is necessarily independent of absolute time Ts. It depends only on the time difference tau. when the time difference tau is 0, that is t2 minus t1 equal to 0, it is the expectation of x of t into x of t gives you expectation of x square of t, that is equal to sigma x square plus mu x square. If x of t and y of t are two random processes and are jointly wide and stationary, then we define expectation of x of t1, y of t2 is equal to expectation of product of x of t, y of t plus tau. Expectation of y of t1, y of t2 gives you expectation of y of product of y of t, x of t plus tau. Next we are going to study on autocorrelation and cross-correlation, the correlation functions. First we study about autocorrelation function. The autocorrelation function of the random process is Rx of tau is equal to expectation of x of t plus tau, where t and tau are arbitrary. The autocorrelation function evaluated at 0 is the average of the random process squared. So Rx of 0 gives you the average power, sigma x square gives you the average AC power, mu x square gives you the average DC power. From the previous slide we know that Rx of tau is equal to sigma x square plus mu x square if the tau, the Ts value is equal to 0. So here sigma x square will give us the AC power, mu x square will give us the DC power. Sum of these two will be Rx of 0, which will give us the average power. So therefore we can write Rx of 0 is equal to expectation of x square of t, that is equal to sigma x square plus mu x square. If minus tau is used instead of tau, then we can write the autocorrelation. Rx of minus tau is expectation of x of t minus tau. So we'll put t minus tau is equal to t dash, then Rx of minus tau is equal to expectation of x of t dash plus tau, expectation of t dash. So, but it is same as Rx of minus tau is equal to expectation of x of tau dash, t dash into expectation of, into x into t dash plus tau. Therefore, we can always write Rx of minus tau is equal to Rx of tau. Thus, autocorrelation function is an even function of tau. Let us now consider the cross correlation. Suppose x of t and y of t are two random processes and are wide stationary. Their cross relation functions are also defined as Rxy of tau is equal to expectation of x of t, y of t plus tau. So Ryx tau is equal to expectation of y of t, x of t plus tau, where t and tau are arbitrary. For cross correlation, Rx of minus tau is equal to Ryx of tau. If y of t is periodic, if there is t, then we write this Rxy of tau plus t is equal to Rxy of tau. If x of t is periodic, if there is t, then Ryx tau plus t is equal to Ryx tau. There are two bounds on a cross correlation function. Expectation of x of t plus or minus k times y of t plus tau whole square is always greater than 0, where k is arbitrary real constant. On expanding the equation, we have expectation of x square of t plus or minus 2k x of t y of t plus tau plus k square y square tau t plus tau, which should be greater than or equal to 0. So expectation of x square t is equal to Rx of 0 This is a constant term, so plus or minus 2k. This gives us rxy tau, and it is k square. This is ry of 0. This statement Rx of 0 plus or minus 2k Rxy tau plus k square Ry of 0 should be greater than or equal to 0. If you assume k value equal to 1, then this equation reduces to the form Rx of 0 plus or minus 2 times Rxy of tau plus Ry of 0 should be greater than or equal to 0. When we simplify this, we get Rxy of tau is less than or equal to half of Rx of 0 plus Ry of 0. Similarly, we can write Ryx of tau, the modulus of this, should be less than or equal to half of Rx of 0 plus Ry of 0. If k is positive real constant, then we can write this as Rx of 0 plus 2k times Rxy of tau plus k square Ry of 0 should be greater than or equal to 0. So the main observation what we have to make here is this quadratic will never be negative if it does not have even roots. The discrepance is such that 4Rx by whole square of tau minus 4Rx of 0 or y of 0 should be less than or equal to 0. So therefore, we get modulus of Rxy of tau should be less than or equal to square root of product of Rx of 0 Ry of 0. Similarly, absolute value of Ryx of tau should be always less than or equal to square root of the product of Rx of 0 Ry of 0. The geometric mean is stronger than the arithmetic mean, so therefore square root of Rx of 0 Ry of 0 should be less than half of Rx of 0 plus Ry of 0. So this is the arithmetic mean and this is the geometric mean. This geometric mean happens to be always stronger than the arithmetic mean. A cross covariance function can be defined here as T of xy of tau is equal to expectation of x of t minus mu y of t plus tau minus mu y. That gives you Rxy of tau minus mu x mu y. Similarly, we can obtain the cross covariance function Cyx of tau. It is expectation of y of t minus mu y, expectation of t plus tau minus mu x. That is Ryx of tau minus mu x mu y. Thank you. In the next video, we will study more about the basic fundamentals of random process by solving some problems.